Hey students, let's take a look at today's lesson. It is the 23rd of February. Well, we're almost done with February. So we're going to start out with this do first. Make sure you grab your Desmos today from your teacher. Make sure you have this do first up. And what we're doing is we're comparing these functions here, right? Which function is arithmetic, which one's geometric, and then there's two of them that are neither arithmetic or geometric. So let's get them laid out. How can we determine what they are? Well, remember, you're looking for that common difference or that growth factor. That growth factor we also call the common ratio. So I'm just going to put these in order here. Take a moment, try to figure out, is it growing by the same number, adding or subtracting? Well, then it's arithmetic. Is it growing by multiplying by a number or multiplying by a fraction, right? Then it's geometric. All right, so take a moment, pause, and try that. All right, so I'm trying to grab a sketch of these. You should see some of these fairly easily, right? If you're looking at this one right here, where are we at? Sorry, I'm zoomed out a little bit too far. You can see that this is going from 50 to 45 to 40 to 35. So that's going down by 5 each time. And if it's going down by 5 each time, right, that is an arithmetic sequence. So we're just going to put a little a right next to that one. So this is an arithmetic sequence. Take a look at this one right here, right? We're going from 4 to 16, 16 to 24, or 16 to 64, 64 to 256. How do we find what that is? Well, I can see 4 to 16, right? We are multiplying by 4, because I can take 16 divided by 4 and I get 4. 64 divided by 16 is 4. So I can see that that common ratio, right, that growth factor is 4. And so that is a geometric sequence. Right here we have another geometric sequence, 1/2 to 1/4. What we're doing is we're multiplying by 1/2 each time to get from 1/2 to 1/4 to 1/8 to 1/16. All right, see if you can find one or two more that match either geometric or arithmetic. All right, go ahead and pause. So as you look through these, you should see there's 2 arithmetic sequences, 3 geometric, and 2 neither. So this one's being multiplied by -2, so that's why you see that going back and forth between negative and positive. 4 times -2, -8 times -2, 16 times -2. This other geometric sequence that we did, and then both of these are multiplied by 1/2. It's just this one's starting at 100, right? This one's starting at 1/2, but they both have that same growth rate or ratio, common ratio. These are neither, right? This one's going down by 1 more each time, so -2, -3, -4. This one's going up by 1 more each time, +2, +3, +4. So those are neither arithmetic nor geometric. Make sure you have those answers correct. Go to the next slide and look for the fireworks to make sure you got them right. So we're going to skip ahead to our goal here on slide 8. We're trying to develop functions to describe sequences. So we're going to see some different patterns, and we're going to try to put those together here. So here's our agenda, and go ahead and let's look at this function notation review here on slide 10. Okay, remember, we've been graphing these slope-intercept lines, y equals mx plus b. We can replace y with f of x, and we get our function f of x equals mx plus b. Nothing changes, it's the same idea, but this is called function notation. We looked at this earlier this year, it should be a review. I want you just to look at this example here. If we have the function f of x equals 4x minus 5, what is f at 3? Right, so we just replace x with 3. That's our input value, right, 3. What's our output? Well, we work it out, and we get f at 3 is 7. 4 times 3 minus 5 is 7. And so we have this ordered pair 3, 7. Input of 3, output of 7. On our graph, 3 would be our x value, 7 would be our y value. Nothing's changed, okay? So then go here, test yourself. What is f of 10? So you should set up your equation. F at 10 equals 4 times 10 minus 5. And then you just work through that. 4 times 10 is 40. 40 minus 5 is 35. And so f at 10, or f of 10, depending on how people say it, you get the ordered pair 10, 35. So my input is 10, my output is 35. You go ahead and try it here on 6, pause it, and then come back. And then go ahead and try f of 0, and we'll look at those. All right, so here's the word solution. Did you get at -6, we get -29? I hope so. If not, just pause it, walk through this, right? When we plug it in, you get -24 minus 5 is 29. And then down here, f of 0, you should have gotten 5. Now, when we have 0 for our input value, remember, what do we call this? Well, that's our y-intercept. We also call it our initial value, right? The value that we start with. That plays an important role in writing these equations, all right? So walk through that, rewind it, check it. You need to be able to do this. So our first idea today is we're going to write a function from a table. And so in order to do that, we need two pieces. First, we need the rate of change. Second, we need the initial value. And so these are arithmetic sequences, okay? And so we're going to create a function from an arithmetic sequence. And so we're going to see how did they increase from 7 to 13, 13 to 9, 19 to 25. We can see it's going up by 6 each time. All right? And so yesterday, that's what we noticed. That's our rate of change is 6. Now the initial value, right, that's our y-intercept, or our initial value. So that's right here, okay? Our initial value comes from this. So our initial value is 7. So our rate of change is 6. Our initial value is 7. We're going to write our equation using this idea that our function of x equals the rate of change plus times x plus the initial value. So we get f of x equals 6x plus our initial value of 7. Now, does this look, oh, I said c, it should be f. I have x because that's what I define my variable as. This should look a lot like our linear equations that we've been writing. We can graph this. It has a slope of 7, a slope of 6, a y-intercept of 7. We're not doing a lot of work here, right? We're not changing it up. We're just writing functions for linear sequences here, our arithmetic sequences. All right. So here it's your turn on slide 12. Go ahead and try this out. Find the rate of change, also known as the slope, and find the initial value, also known as the y-intercept. Take a moment, try this out on your own. All right, were you able to find f of x equals 2x minus 9? Okay, that 2 is our rate of change, right? We're going plus 2, plus 2, plus 2, all the way, right? And so we can see we have that constant growth, right? That rate of change of 2. And then we're starting when x is 0 at -9. So now let's do it from a sequence. Well, in order to do this from a sequence, it's just a list of numbers. When you get a sequence, this first number is always your first sequence. So I'm going to put that here in the table at 2. All right? So we have 2. Our next term of our sequence is 8. The next term is 14. The next term is 20. The next term is 26. By this point, you should kind of see the pattern already, so we don't need to keep going in terms, right? And we can see our rate of change, right? We're going from 2 to 8 is plus 6, 8 to 14 plus 6, 14 to 20 plus 6. So that rate of change stands out. What we don't see is our initial value here. All right, so how can I find what f of 0 is? I know I'm going up 6 if I go to the right. Can I go backwards 6? Yeah, so if we go backwards 6, if we subtract 6, I'm at -4. And so now we have our initial value. So what is our f of x? F of x is equal to our rate of change, 6, times our variable, our unknown x, plus our initial value plus -4. Now I can rewrite this as 6x minus 4. And there you go. We have a function for this sequence, 2, 8, 14, 20, 26. Nice work. So then you try it. Can you write a function for this? Did you get f of x is 5x plus 1? If so, awesome, you did it. If not, join me as I walk through this. Again, the first term of our sequence is 6, so I'm just going to use this table to help organize my thinking. All right? And what I see here is, oh, we're going up by 5 each time, right? We're adding 5 each time. So my rate of change, what I have right here, has to be 5. Now, how do I find this initial value? Well, if I went up by 5, I just go backwards by 5 and I get 1. And so that's where my 1 came from. Any more questions about this? Join us in office hours. This looks familiar. So now we're going to just take a tile pattern and we're going to create a function for this tile pattern. Well, how many tiles are there here? 1, 2, 3, 4, 5, 6. Still 6 plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right, so this is 11. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So my first figure has 6, my next figure has 11, last figure has 16. My fourth figure would probably have 21 if I wanted to find it. What does the 0 figure have? Well, I would go backwards 5. Hey, this table looks awfully familiar. If you click back, look, it's the same table. Guess what? It's going to be the same exact function. F of x equals our growth, right? Our rate of change, 5, x, plus our initial value, 1. All right, so you're going to try. Go ahead and check this one out. So hopefully you paused and worked through this, and hopefully you came up with f of x equals 3x plus 5, right? My initial value of 5. I'm going up by 3 each time, so that's where that 3 comes from. All right, so go ahead and fill out what are the parts you need to write a linear relation or a function for a linear relationship for these arithmetic sequences, right? It is what? All right, you need that rate of change and you need the initial value. Well, this doesn't change much when we're talking about writing exponential functions, right? These geometric sequences creating exponential functions, we're going to follow this pattern right here. F of x equals a times b of x. A stands for our initial value. Sound familiar? And B stands for our growth factor or common ratio. And we found those yesterday in class, right? What is the growth factor or common ratio? It's that multiplier. All right. And so if I'm looking at this graph right here, notice I am crossing the x-axis right here at 0, 1. And so my initial value is y equals 1, right? My a value is 1. And then look what's happening. If I plug in a 1, I get a 2. If I plug in a 2, I get a 4. Input of 3, I get an output of 8. Input of 4, I get an output of 16. And so I wrote that function for you right here. The initial value is 1, right? 0, 1, so my initial value is 1. And then my growth factor, it's going up by 2, right? 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. And so this is the exponential function for this graph. All right? Soak that in, write this down, make sure you have these in your notes, and let's practice this next one together. All right, 1 minute left, so I'm going to go kind of quick. All right, what we see here is I'm doing what to go from 1 to 3, 3 to 9, and 9 to 27? I'm multiplying by 3. So my growth factor is 3. My initial value, same idea. When x equals 0, what do I have for my initial value? I have a 1. So my initial value is 1. If I type out this function, f of x equals 1, I do the little star above 8, shift 8 to get that dot, the multiplication sign. My value is, growth factor is 3, and then I hit shift 6 to get my exponent, and it's to the x power. So f of x equals 1 times 3 to the x power. And when I plug in 1, I get 3 to the first power is 3. When I plug in 2, 3 to the second power is 9. Plug in 3, 3 to the third power is 27. And 3 to the fourth power is 81. Try the next questions. The homework's at the